Okay, we're back to this thing. So this is my 74HC595 project, well, a project, which I'm not entirely sure why I'm doing this, because it's kind of like, well, I've explained everything, but I kind of want to go through this because I think this is interesting for the, oh, I've still left this bit here on, sorry. This is my random astable multi-vibrator, which I just stuck in, which didn't work. But we'll come back to that later on. So this is actually going to end up being a slightly involved project that is going to be kind of interesting. So we're getting to the we're getting there. It's going to take a while though, and I'm hoping that we can do everything with that little, all the bits that came in this little kit set thing, mostly, except for the wires and the power thing. But anyway, so I've changed it slightly, and the one thing I've done is I've gone back to our old friend the 4050, and I've stuck one of those in there. I actually bought a packet of 10 off the internet, so now I've got a few more. That's just to buffer the signal, because I was having a problem getting everything running off the one clock and having the LED light up properly and not interfere with everything. So this is just buffering all the signals. So what's actually happening is the clock signal is going in through here into this bit here, and then that's being sent off to two different bits over here. Actually 3, and so the signal's being sent to 3 inputs on the 4050, and then those the outputs from those things are being sent onto the various parts of the rest of the circuit. So just so that what the LED is doing isn't causing a load for this thing here, which is why, I don't know if actually you can see that on the previous videos, but the LED would get dimmer the more of these things were lit up. And it also, well, as I was working on it, it all caused lots of problems. So these are bypass capacitors that I don't know if I really need, but I just chucked them in anyhow. We're not going to talk about those today; they're not relevant. But anyway, we'll start it off and we'll see what we get, and we get it kind of working. So it starts off with the random sort of data. So we're back to where we were before. It's going quite slow, and there's a reason for this. So we aren't going to change the functionality exactly, but we are going to talk about this little problem that we had that I keep mentioning. I saw that Julian person, he had a video about this, and he mentioned the synchronization problems that you get. And that's what we're going to talk about today, and we're going to talk about a couple of solutions to try and get around this. And the problem comes down, so I'm going to try and explain what the problem is, and then try and illustrate it, which is going to be difficult, and then try and come up with some solutions, and then there'll be a follow-up video where we try and test whether or not the solutions actually work. So anyway, here's my little picture, first picture. I'm going to move this out of the way. So this is kind of what my representation of what's going on inside of the 74HC595. I'm just going to call it the 595 from now on because it's too long. But anyway, you can see, so this is meant to be, the important thing about this chip is that there are two things called registers. Registers are just like the storage of values, and I've put zeros and ones here, but this is basically highs and lows. So it's a high voltage, low voltage type thing, but you know, basically these are all used for like things like computers and stuff, and we all think in zeros and ones, so I'm just going to put 0 and 1s. So 0 means low voltage, 1 means high voltage. These things are all kind of interchangeable in this context, of course. So at the top I put A, B, C, D, E, F, G, H. Now these don't actually represent anything. They were just like, they're just fixed values. So A is either a 0 or 1, B is a 0 or 1, C is a 0 or 1, and D is a 0 or 1, and so on. But they don't change in the context of my little pictures. And that's all that matters. That will become apparent in a second. So initially it starts off, one register is what's actually being output at the pins, and so this is the important part. So there's the output pin register, and then there's the internal register, which is the thing that you actually do the serial shifting on. So when we send a clock pulse to the latch pin, which is not labeled that on this thing here, it's labeled R clock. I think it's R clock. I don't know what the R stands for. I was supposed to look up a different data sheet, or look up the rest of that data sheet and find out. But anyway, all that matters is that there's a latch thing, and the latch thing latches the internal register to the output register here. So when you do this clock where it goes to a positive, goes from low to high, all the values that are in the internal register get copied across basically to the output. So if this was A was a 0, then that 0 would appear there. So that's the basic bit. Now the tricky part comes is, so here, what have I got? So here's my latching, it puts everything on the outside. That's just a repeat of the last bit. But what happens now is, what happens if, oh, so I see what I'm doing here. I did this yesterday, so I'm not entirely sure that I remembered exactly how I'm going to explain this. But what happens here is, with my current circuit, we are using this clock pulse that's coming from this little pulse generator circuit here, and we're sending it to both the serial clock and the latch clock. So the serial clock, when that happens, when that goes from low to high, everything in here shifts along one. So in my case, I've kind of done it so they shift that way. It made sense yesterday because it's upside down. So when you clock the serial pulse, the inside register, the internal register, moves everything one bit one direction, one space one direction. So in this case here, what was H has now moved. So where H was now, it's gone to here. So if this was a 0, then the 0 is now there, and if that was a 1, then the 1 is now there. So we've basically moved everything along, and I was what was currently in the serial input pin. So if that was a high voltage, then we now have got a 1 in here, and that was a low voltage, we've now got a 0 in here. So we're just shifting that along, and we're doing this. But the problem comes is that if we try and do both these things at the same time, then the latch is done essentially first. Every time I've done this, it comes up first. Now it might actually muck up, and it might actually, I suspect, in some cases, when you do them at exactly the same time, then sometimes it might be sort of, what's the word? Disrupted. That's not the word I'm looking for. Be corrupted, that's the word that I'm looking for, because what might happen is you're halfway through shifting this along, and then you might shift part of it out. But I'm not entirely sure how the shifting operates on the inside, and so it might do it in a different way. So that might not be an issue. I've never seen this actually happen, where it gets half of it copied across and then shifting the rest of it. So it's not an accurate copy, but that is what I am getting a problem with, is that you get an accurate copy of what it was before you do the actual shift. So in this case here, so this is the output. So I'm latching what I had before, which was this thing here, and that's copying it straight to the output. And then we're doing the serial shift of the internal register. And that's not what I want, because I want, after I've done this clocking thing, I want what's internally to be represented externally. Now there are other serial shift chips which make this much easier, because they don't actually have that clocking, where they don't have an internal register, or the latching is done in a different way. But we're going to use the 595 today, and so we're going to try and work out how we can get around this problem here. And so what we really want to do is we want to wait a little tiny bit between the serial clock. So the serial clock is going to shift the internal stuff, so move that along a bit and then put something new on the end and drop off the A, so the A has disappeared. But in our case the A hasn't. The A will actually go back into here. And that also goes back to, so last time I was like, oh, what's the difference between QH- as an output and QH? So I did the letters the wrong way around. So these letters here do not have anything to do with these letters here. So hopefully that's not too confusing, but it will be. So, but I'm sorry. I don't know what other characters to use. But anyway, so the H- is the internal register's end bit. So it's not the external one. So they are different in this case here. So if you're shifting these things along, what this thing is outputting is the internal last bit. So that lets you do the whole shift thing without having to do this. So when you do this on an Arduino or with any other microcontroller, you're going to shift in 8 bits first, and then you're going to latch it to go to the output. So you're not going to be latching it as you shift in the bits. You're going to be doing it like this. And if you're this kind of functionality, we'll come back to this when we talk about how you do it with an Arduino. Though I looked it up on YouTube today, and there were millions of videos on this, so I don't know if that's going to be that exciting. But I guess I should just do one short one, just for the heck of it. But this thing here is for passing it on to the next. So you can have multiple ones of these in a line, and you can continue adding them on for as many outputs as you want. And that one is going to go to the next one, and you're going to keep doing this before you actually update the output. And so you want to have the internal one you know, what do you mean? Anyway, we'll come to that when we look at it. It's not what I'm here to talk about today. So anyway, so what we want to do is we want to basically delay it. We want to do the serial clock. So we want to shift the internal register 1 bit to the left, basically. I'm going to feel like I'm going to end up talking a bit like a computer programmer every so often, because I am a computer programmer. And I would just call that a shift to the left or something, or a shift to the right. And then, so this is my graph of time. So as we move along, so we're moving along here, and right now both voltages for both pins are low. So you have to pretend that there's another little line here, and that these are two separate graphs. I don't want to make them overlap because then it might be a bit confusing. But you can pretend. So this is 0 and 5 volts for this one, and this is 0 and 5 volts for that one. But anyway, what happens is, as you go along in time, the serial clock jumps up to 5 volts, so there's a positive edge on the clock, which is what it's waiting for internally. And so that will shift the internal register, and then a little bit later, and we're talking about a tiny fraction of a second here, it doesn't have to be very long. And we want it to be quite short, because so no one notices this kind of stuff. And then we do the latch clock, so we shift it and then we latch it out. But we don't do it at the same time, so we have any conflict. So what are the ways that we could do this? Now I'm going to go through 3 ways, and I'm probably only going to actually do 2 of them. I don't even know if we're going to get 2 of them done today, so we'll see. The first way that I would do this is to invert the clock. Now I'm not entirely sure if it's that obvious, but you can kind of see that the little blue light is actually flashing and is on most of the time, and only goes blank for a brief second. So in this sort of case here, so which one is the one that I've got? I've gone and flipped it the other way around. Or have I got it upside down? Well, this is probably the clock that's actually coming out of the microcontroller, out of the pulse generator. And so in this case here, it's low for a small amount of time, and then it jumps back up to high, and then goes back down to low, and then jumps back up to high, and then goes back down to low, and then jumps back up to high. So most of the time it's high, but for a fraction of the time it's low. So one way that we could kind of delay things is we could invert the clock, and then we could feed the inverted clock into the latch clock. So to see why this might work, I might have this the wrong way around. No, I don't. This is really only going to work if you have it the other way around, isn't it? Well, maybe in this case here. So before I had a 4049 and these were inverted, and so it made a bit more sense. But in fact we have a long clock. So this is called the duty cycle, I think, of the whole cycle. So that depends on how much of your one cycle. So this is one cycle here. How much of the time are you high and how much are you low? This is what the duty cycle is. In this case here we've got it's mostly high, but we'll just pretend for a second that the pulse is the other way around, and then we'll come back and talk about it. So let's just pretend that briefly it is high and then it is mostly low. So in this case here, if we invert it, so on this point here, this is where the serial clock is going to be read. So this is when we go high, And on our inverted clock, right, it's not going high, it's going low at that point. But a little bit later, when this one goes low, this one goes high. So what's going to happen now is the serial clock is going to clock at this point, and the latch is going to clock at this point. But because I made a mistake, so when I had the 4049 in, which is the same as this one in the pins as the 4050, if you recall that video, so the 4050 is a non-inverting buffer, and the 4049 is the inverting buffer. So when I had that before, it still works fine, doesn't make any difference to anything. But what would happen is that I got this kind of output. But that is fine, because instead of saying, okay, well this is going to be the serial input, this can be, is that going to work? I guess it's going to work. That this would be the serial clock. Yeah, no. No, I've got it confused here because it's upside down and I have to think. So what would happen if you latched on this one and then you did it on that one? No, that's not going to work. Let me just turn this up for an hour for a second so I can think about this. Because it has to work, right? It has to. Like, it's just an inverted clock, so you should just be able to swap them around in this case. Latch serial. Well, that's what I've just got. I feel like it's just because I'm looking at it in terms of... because I can't just keep feeding things in. Well, anyway, let's just pretend the clock looks like this, because this is fine actually, because we're going to get onto a better solution after we've done this one. If we don't, so the problem with this one, of course, is if I don't have this kind of duty cycle, it's not going to work that well. But the one way we could do it is we could just send the clock signal into a 4049 to invert the clock signal, which is fine. We could do that. But we're going to talk about something different today, just to make it a bit different. Because also, if you've got that little kit set thing, this is going all over the show, it's going to make sense when we get to the end. So if you've got this little kit set thing, you don't get a 4049 in this one, and you don't even get a 4050, but we don't need the 4050, just pointing this out, you don't really need the 4050, I don't think, because it's just there to make sure that the light stays on and that I'm not interfering things. So this is just for me to work everything out. But we're going to finish it off with taking the 4050 out. But we don't have a 4049 either. So how can we get an inverted signal? Well, we can do what I think they call Mickey Mouse logic. So we can do another way using the things that we have in here. And the way that we're going to try and do this, so I'm going to reveal and rip the paper at the same time. That was a dumb idea. Alright, we're going to use, I don't know what, I think it's just called Mickey Mouse. I don't know why it's called Mickey Mouse logic, but it's just, you know, little hacky things you can do. But this is not too hacky. So we're going to use a transistor. So we're going to use an NPN transistor, and these things come with a couple of 2N222s. I think that's what they are. And these are very common transistors. They always come in everything. And so these are sort of like good use for these with digital circuits. They work well with these kind of things. And so how it's going to work is this. So we're going to kind of be going back to our pull up and pull down discussions from before. So this is the pin here. This little part here is the IC, the 74HC595 that's over here, and this is the latch clock pin. So this is our clock according to the diagram, the manufacturer's data sheet. And so by default we've got like a pull-up resistor. So this is probably, I don't know, 10. We'll just say it's 10k for now. Or 100k or whatever, and it's coming from the positive voltage and it's going in there. So if the transistor isn't doing anything, if it's not engaged as it were, it doesn't really count. And so you've got this here, and going back to our pull up and pull down resistors, this is going to create a voltage divider with this internal part here. So this has an internal resistance which is hugely high, and this is, doesn't matter what this is, it's nothing compared to this. So the voltage at this point is going to be a high voltage. Okay? But if we have a transistor in here, and then we have if we put a high voltage going along this part here into the base of the collector, base of the transistor. So we haven't talked about transistors yet, and we're going to. So I'm assuming for this video you roughly understand a little bit about it. So if we put a voltage into here, a higher voltage than ground, into the base of the transistor, this will activate the transistor, and it will create a pathway down to ground. So as long as this is high enough and there's enough current flowing through here, then the voltage across the transistor will be very low. It will be like close to zero. Like I think it's 0.3 is the minimum or something apparently, but my meter says it will be 0. So my meter obviously isn't very good. And so what you'll get is this will be pulling it down to ground, and so this thing will read a 0 when you put a voltage through here. And when you don't put a voltage through here, this transistor isn't turned on. So when you've got a ground voltage or a low voltage, this transistor doesn't get turned on, and what you get is the high voltage from here. So if you're putting the clock, your basic clock signal through here, say this clock signal is high, this turns the transistor on, that pulls it down to ground. So there's a much better path straight to ground. And you don't have to worry about blowing up the transistor because the voltage is going through this resistor here. So it's not stressing out the transistor in any way. But if this is low, so this is a low voltage, then this transistor won't get turned on. And so you'll get a high voltage. So when this is low, this is high. When this is high, this is low. So you've created yourself an inverter. And so the best thing right now, because I don't think we're going to have time to actually try it out, but I'm going to try it before I do anything, before I forget. I don't know if we're going to even have time to show it. But I want to show why it doesn't work. So if you watch these things here, we're going to clear it off. Alright, and we're going to start with 1. Alright, so what should happen is when I get to just before here, and this one is still off, and then I hold down my button, the next time it shifts, I should see 2 LEDs on. So if you get what I mean. So if this one's there and then I hold that one down, then that blank one should become on the next time it moves through. But if I do that, so you're going to have to trust that I'm pushing the button. So I'm going to push the button when the light is on this one and not on the end one. And then if it works, I should get 2 LEDs on at the same time. And if it doesn't work, I'll get 1 LED on at the same time. And the reason that I'll get 1 LED on at the same time is because the output is one step behind what's actually happening on the inside of the chip. And so on the inside of the chip, when this LED is actually lit on the inside, this is the pin that has a high, this is the part of the register that's high. And so when I hold the button down, it's already high, and so I'm just turning it to high the next time. And in fact, if I hold down the off button when this one is lit, then the next time it will turn that one off. So you should see what I mean. So first off, I'm going to turn that. Oh, I did it wrong. Okay, I'm going to wait for it. Button down, and put 2 on. I think that's not very useful, is it? It's not supposed to work. I had this problem beforehand, is that sometimes it worked and it wasn't supposed to work. So I'm going to turn this off again. It's not supposed to work. It didn't work that time. Alright. Alright, so turn one on and we'll try it again. So hopefully it doesn't work this time. I did it wrong again. It still didn't work the way it's supposed to. Alright. Alright, turn it off. Actually, that was the wrong way. So here we go. It's very hard to do. I tried to make it as slow as possible. And now, oops, I did it wrong. Okay. And now. And you can see it didn't actually, so I got it right. It doesn't actually work. So this is frustrating, right? Because it's very hard to show that it doesn't actually work. And it's hard to even notice sometimes that it doesn't work. And it's certainly hard to notice it when it's going really fast. It doesn't make any difference. But trust me, it doesn't work at the moment. So we're going to try and the few minutes we've got left to make up this little inverter circuit, and we're not going to plug it in straight away today because I don't think we'll have time, but we're going to put another LED on, and that's going to, so where's my, we need another little board. Sorry, I've got a spare one here. Alright, so we are going to first off put that one there. Hold on. I knew this was going to take a very long time. So I'm going to have to get my little book out to find out, which is right here of course, what the pins are for the 4050. So the way we're going to do this, we are going to buffer the signal, because this little trick here doesn't really work unless you're using these CMOS inputs. And so here's my little book, and this is the pin outputs. So I've actually used, I'm going to have to put it this way around, sorry it's upside down, but this isn't for you, this is for me. So that's the power. So this is going to be the output, and this is going to be the input. So we're really running out of room here. Alright, so the output, let's make sure we've got this the right way around. And we're just going to quickly hack in the power rails. Oh, this is such a mess. I think this is partly why I get a bit disheartened by the whole thing, is that you really do have to do a good job of these things, and I'm not really doing a good job of these things. And so, alright, where we have to link up the grounds across here. So the ground goes across there, and we're just going to use, so these are the little things. So I put little numbers on the side. So where is a low one? What's this one say? It says 100 ohms. Oh, we're going to run out of time. When you want a whole bunch of resistors, they all just disappear. What's this one? Who knows? That's way too high. Well, we'll just do this one. It's fine. It doesn't matter. Okay, and then that one is going to go to low. So right now it's giving out funny outputs because it's not actually connected to anything. So this should go high and then off. So now it's connected. So we've got to get this thing here to be, what time have we got? 1 minute. We're not going to have time. Alright, well we'll just have to do a follow-up video for this. So we'll just get out my little transistor. Alright, I'm going to finish the video here and then I'm going to start a new one, and then we're going to, well look at that, it's flashing, it's picking up the pulses somehow. That's kind of cool. This is plugged into the right thing. Well, that's neat, isn't it? So look at that. It's kind of like radio frequency transmission. Alright, I'm going to stop the video and then I'm going to come back and we're going to get this working, and then I'm going to finish it for the evening, and then we're going to do the more exciting stuff tomorrow. So thanks for watching if you're going to finish now, and I'll see you in a second.